Hello, everyone. Miss Peachy again from WCA Physics, and today I am going to go through your lesson here on displacement and distance. So, hopefully, after we go through this, you'll have a better understanding of this lesson. This is pretty important going forward because we're going to be starting kinematics, which is basically looking at, it's kind of a study of a object's position in space, really, because we're looking at kind of, you start off with distance and um, speed and velocity and acceleration, and you can combine all those and you can predict where something is going to be in space. If it's like moving at a certain velocity or if it's been, you know, projected, a projectile is launched at a specific angle. So there's all sorts of things you can do when you're using kinematics, but we start with kind of the simplest stuff, which is just understanding what displacement is, what distance is, what vectors and scalars are. So our keywords, displacement and distance, and we'll go through the differences between those two in a moment here. Magnitude, resultant vector, scalar, and vector. So those are our vocab terms. And some of this might be familiar with you, but I beg your patience with me while we kind of go through it because, like I said, they are very important concepts to build upon for the future, and it does get quite a bit harder. So understanding this is pretty vital. All right, so the idea about this concept is that there's a difference between displacement and distance, right? So distance is just kind of a total amount of time or total amount of travel that you've had, whereas displacement is a difference between your starting position and your ending position. So when we look at here, it talks about a scalar quantity. When describing the motion of an object, sometimes it's useful to know how far it has moved regardless of its direction. This is an example of what's known as a scalar quantity, a numerical value with a magnitude but no associated direction. Other times it's helpful to know an object's direction of motion, in this case a vector quantity or a numerical value that has both magnitude and direction is used to describe an object's motion. Examples of scalar quantities include volume of a cube, temperature, time, and speed. Vector quantities tell more information about an object because they include direction of change. So, vectors can show how far an object has moved and in which direction. Vectors can be used to show how other quantities change too, such as an object's speed. Speed by itself is a scalar quantity, but velocity is a vector quantity, which I'm sure some of you may have known that already because we kind of harp on that a lot in physical science that, speed is scalar. We might not use the word scalar, but the velocity difference between speed and velocity is that velocity includes direction and speed does not, right? All right, so some introductions between the difference between scalars and vectors. Now let's look at displacement versus distance. So distance is a scalar quantity and displacement is a vector. So distance is including just the magnitude, no direction, whereas displacement includes both direction and magnitude. So the difference, we can kind of look at it this way. Suppose a helpful teacher, I'm going to make that me, walks from her desk to at point A, over to the globe, which is directly east at point B. It's helpful to think of an object's starting point as the origin on a number line. Because vector quantities have magnitude and direction, they are indicated by arrows to show the direction of motion. So I'm just going to stop reading right from the slide. But if this is me, point A, and I'm going to the globe for some reason. So maybe I want to show you something on a globe, point B. If I want to just know how far I've traveled in distance, I'm going to measure the distance from A to B, because I'm going to go this direction, and I'm going to turn around and come back, right? So my distance is my total amount I've traveled. Say this is 5 meters. 5 meters there, 5 meters back. So I've traveled a total of 10 meters, right? Displacement is a vector quantity. So direction matters. So when you look at the displacement of something, you're actually looking at its initial position and its final position. So displacement we use the denotation delta x. You're going to see that before, or you'll see that later. I don't know if you've seen it before. I would be a psychic if I knew that. So delta x, delta, and this one, by the way, this is uppercase delta. I was not familiar with lowercase delta earlier. So uppercase delta x here means change in. So delta in this regard with a little triangle symbol always means change in. So change in position. That's x. We're doing horizontal position here, right? So we're moving horizontally, we call it x. If we were moving vertically, we would call it y because we'll use that Cartesian coordinate system that you're familiar with, the xy coordinate system. So we have our difference in position. So we call our initial position over here at A, we call this, let me use a different color, red. We call this x sub I, which stands for initial position. And then we call this x sub f, which is final position. Some sites and sources and textbooks and stuff, instead of using I and F, will use 1 and 2 here. So initial being 1, final being 2. I actually like the I and F best. That's kind of my favorite way of looking at it. You'll also see this just for future reference. Sometimes they use X naught. 0 being called naught, meaning that that's my initials where I start at. So again, I actually prefer the X sub I and the X sub F, and I'm glad that this curriculum is using that because that's what my preference is as well. So delta X over here, and I'm going to rewrite this without the little sparkly pen. I like the sparkly pen, but it's not as easy to see. So delta X is equal to my final position minus my initial position. In this case, if I look at my final position, which is B, that's positive 5, or that is going to be 5 meters from A, right? So if I start there and I'm going from A to B, because in their example, they just went from A to B, they didn't go back. Oh, let me go back. My example, I started A, which was 0. I just screwed up there, so I just started over. So my initial position was 0, and my final position was 0, right? So my delta X is 0. Even though I actually walked 10 meters, my displacement is nothing. I've not gone anywhere. I'm still in the same place I began, right? So the distance I traveled was 10 meters, but my displacement, my total displacement was 0. All right. So that's pretty simple, I think, when you're looking at a straight line like this. It becomes very, very, very simple. But very oftentimes we aren't just walking in straight lines and walking back in straight lines. I would say more often than not, we don't do that. So we look at 2 dimensions. So we're looking at our x, y coordinate system now. So let's just draw that on here. There we go. So with our x and y coordinate system, we have 2 dimensions of travel. And you can see this picture over here, right? And so what we do is we have to figure out like our final displacement. It becomes a vector problem. So if I traveled from 3 meters this direction. And then I turned and went 4 meters this direction. We want to know what's the total displacement. And we do this by drawing a resultant vector. And our resultant vector is drawn as the hypotenuse. I think, let's see if I can do this, to this triangle. And sometimes we call this is our, I might just call it D for displacement. I'm trying to see if they used a different variable here, but they didn't. All right. So basically, what you can do here is you can do, well, they use different numbers, but you can do the Pythagorean theorem to figure out your total displacement. So here, we started at 0 and we went to 3 meters, right? So we have 3 meters there. So they're going through this whole step here, which you can do, I guess. I feel like it's kind of unnecessary. Oh, they're doing that. I'm sorry. My bad. They're looking at total. This is distance traveled over here. So what's my total distance traveled? Well, I went 3 meters plus 4 meters. So I want a total of 7 meters, right? That's the distance I traveled. So my distance is always just a sum of the different lengths that I'm traveling, right? My displacement, this is where I use the Pythagorean theorem because we have a right triangle here. So I'm going to use Pythagorean theorem and say 3 squared plus 4 squared equals d squared. So 9 plus 16 equals d squared. This is a perfect triangle on purpose just because the math's easier. They won't always be perfect triangles. So 25 equals d squared, square root of both sides. D is equal to 5. So that's my displacement. So my displacement is 5 meters, but I'm not done because I also need the direction of travel, right? I need the direction here. So I'm just saying what they're doing here. So we're going, so you would be able to figure out the direction here. You need this angle here to figure out the direction. And you can do this using SOHCAHTOA. They're not actually getting into this yet, so I'm just wondering if I should even go this far. So we'll hold off on that for now because you can figure out the direction too using SOHCAHTOA, your sine, cosine, tangent functions. You can actually use those then to figure out the direction that you're traveling as well. And that's something you're going to have to do. But the lesson at this point isn't actually doing that yet. So we're going to just kind of foreshadow that for the future. That's something you'll have to do in the future. But for now, we'll kind of just lay low on that and not teach a new skill until the lesson teaches that new skill. Okay? So yeah, that's pretty much the difference between distance and displacement. And just a very, very, very introduction into these vector problems. Again, we've solved for the displacement quantity portion, the magnitude, but we did not solve for the direction yet. You would have to use your sine, cosine, tangent functions. You've got all the sides of the triangle, right? So basically, you're just going to have to do the inverse of one of those to be able to get the angle here. So hopefully that makes sense. We'll do more of that in the future. So again, I'm not going to add that right now just because I want to make sure we're kind of sticking real close to what the lesson's teaching. But, stay tuned because that's coming next. Have a great day, everybody. And again, let me know if this is useful.